Hi, I'm Hyun-Kyu Kim from Yonsei University. Today I'll present our work, AcTTA, Rethinking Test Time Adaptation via Dynamic Activation. Deep models are trained on created data, but at deployment they meet conditions that rarely match the trained distribution. This mismatch, known as distribution shift, can significantly degrade performance on the target domain. The goal of our work is to recover that lost performance at test time. The most representative form of this is covariate shift. The input distribution changes between training and testing, while the underlying class relationship stays the same. A dog is still a dog even under fog, noise, or a new sensor. The challenge is that the model's features no longer sit where they did during training. Test time adaptation tackles this directly. Following intent, the model is updated online, one test batch at a time, with no access to source data. The objective is simply entropy minimization over the model's own predictions. The key question is, what should we update? Almost all prior works update affine parameters of normalization layers. And that's where we step back. Most recent works focus on normalization, but normalization only recenters and rescales features. The component that actually decides how features respond, the nonlinearity, is left completely fixed. So we ask, could the nonlinearity introduced by the activation be a more direct and more critical lever for handling distribution shift than normalization alignment? Learnable activations like PRELU, PAU, and ACON already exist, but they were designed for source training to add expressive flexibility, not for stable online adaptation. More importantly, their response stays anchored to a fixed zero-centered boundary, which is exactly the wrong assumption when feature distributions have shifted. So we design an activation with three properties. First, deployability. It must plug into any pre-trained model and exactly recover the original activation at initialization. Second, center shift. It must move its response boundary to align with the shifted feature center. And third, differentiability. It must stay fully learnable for stable gradient updates. In short, we adaptively control the left and right slopes and the center, starting from the source model's own activation while avoiding dead gradients. Here's the formulation. Most modern activations can be written as x times sigmoid of beta x. We expose its slope as a learnable function with separate negative and positive slopes, and add a learnable center c. Combining the two gives our activation of g of x, a shifted base term plus adaptive slope modulation. When the slopes and center are all zero, G exactly equals the original activation, so adaptation emerges naturally from a perfect starting point. We evaluate on the standard corruption benchmarks CVPR10C, CVPR100C, and ImageNetC, using 15 corruption types at the highest severity, level 5. We compare against 6 representative TTA methods from 10th through ROID and CMF. Crucially, all of them were designed to update normalization parameters. We evaluate each one instead or jointly on our activation module, so the comparison is apples to apples. All numbers are error rates, lower is better. Two findings. First, the best adaptation target depends on the backbone. First, BN-based CNNs, adapting the activation alone works best, while for layer node-based VITs, normalization and activation works best together. Second, against prior learnable activations like PRELU, ACON, and PAU, AcTTA wins clearly, which tells us the center shift mechanism is doing real work under distribution shift. Because AcTTA is just a plugin module, we add it on top of every baseline. Across many of datasets and architectures, it shows meaningful improvements. This shows activation adaptation is complementary to normalization-based TTA, not competing with it. Over the long horizons, normalization-based methods drift and forget the source. By limiting adaptation to the activation space, AcTTA gets the best target performance while preserving source far better than Tent Continual and COTTA. Looking inside the adapted model, we see the learned activations generally change. For both ReLU and GeLU, the center shift and the slope profile adjust after adaptation, exactly the behavior our formulation was designed to enable, and it emerges on its own. AcTTA reaches the lowest error while using far less memory and runtime than heavy methods like ROID and CMF, and also improved gradient flow during adaptation. To conclude, AcTTA moves the adaptation target from normalization parameters to the activation function itself through sensor shift and asymmetric slope modulation. It's stable and broadly effective across small batch, large batch, and continuous settings. Our main limitation is that the best design still depends on backbone, activation type, and depth, and a fully principal selection rule is future work. Thank you for listening. Please visit our project page for details and feel free to reach out with any questions.